Hey Jillian. So I'm gonna answer your question with this little mini lecture. So just listen up. So, and this doesn't matter if you do or do not have either of these. I mean, obviously you should have Excel, but you should have access to Alcula as well. So if you do have by chance this calculator, I'm gonna work out your example. This obviously has to do with five individuals or five data collection points with two outcomes. So there's an X and a Y, some sort of correlation, not necessarily causation. So these are your X values, and I'm going to input your Y values here. Alright, and what I want you to see in particular is the numbers that come out. Watch. So I'm going to go to stat, I'm going to go over to test, and I'm going to go over to line rec t-test, which is right here. All I have to do at this point is hit enter, make sure that I have X in list 1, Y in list 2, frequency. This has to be not equal to because we're trying to prove whether it is a good model or not. You see this p-value right here? You see the p-value of 0.002? That's a very small p-value. Okay, and so if I scroll this value down, you'll see there's your equation. A plus bx. A is 31.7. That's your y-intercept. That's where you start if x is 0. And the b value, well, this is your slope. You notice it's a negative 0.467. You could stop there. And this is your standard error at 0.191. There's your coefficient of determination, which is predicting the effectiveness of the model. And there's your R, which is also negative 0.985. Just remember, the slope is negative, so is your correlation. So what I'm going to do to sort of pair this up so you see what I'm getting at with Excel is in Excel, you have your values, your 58, your 59, 61, 62, 63. And here's your 4.5, here's your 4.2, here's your 3.4, here's your 2.5, here's your 2.3. Okay, so I have, in a sense, what we would consider an X value and a Y value, okay? And what we're going to do is we're going to use the Excel functions to replicate what the calculator just gave us, right? And so let me just, I'm a little neurotic, so I like aligning things up a little bit. So let's see, we want the center. There we go. Alright, so let's say I want the slope. In Excel, you simply say equals SL, and there's your slope. Double click on it. You see how it asks you for the known y's? Highlight just the numbers, comma, and now it wants the known x's. Enter. That's your slope. That's exactly what we had in the calculator. So let me go back to stat test. Line rec t-test. It's going to ask you to go through all this again. And you can clearly see that that was our slope. Alright, we want to repeat that process for the y-intercept, which is our value present, whether or not x is 0. If x is 0, this number would exist. So notice that y-intercept, highlight the known y's, comma, highlight the known x's. It is very sensitive, so you have to make sure you have the equal numbers. So that means that our predicted equation, our predicted y, is equal to 31.7 minus 0.467, and then your variable, independent variable x, which is going to sit right next to it. I'm going to put another parenthesis here just for the sake of clarification. So The way it works is the formula, predicted y, you would need to input values into x to determine, what the predicted value would be within the allotable numbers. So we have two terms to keep in mind. One of them is called interpolation. The other one is extrapolation. Interpolation is reliable because interpolation says the x values are within 58 to 63 inclusive. So we're okay there. Extrapolation is anything other than the values above. So it's either outside the range that we have. So for example, an example of an extrapolation would be if I substituted in, so let's say I substitute 75 as a number in for x, so equals x. Then I have a problem because that model, if you notice our model only goes from 58 to 63. And so that would give us a predicted y. So for example, if I'm looking at this as an equation, so let's go over here, and I'm going to say you're equal to 31.7 minus 4.67 times, and let's select a value, say in this cell, enter. Okay, so at this point, this value is 0. If I plug in a 1, see how it changes? If I plug in a 2, see how that changes? Here's a green, right? So if I plug in 58, my predicted value is that. If I plug in a 58.5, I'm still interpolating, or within the interpolation. If I plug in 62.9, I'm still within the range of x values from 58 to 63. Extrapolation is what I was doing initially, which is, okay, so what if I plug in x is 6? That's way smaller. That has nothing to do with our model. So a 0.045 would be an extrapolation. We wouldn't consider that to be a viable number to substitute in, because our model is based on x values from 58 to 63. Now, alcula.com is a website that I also referred you guys to as a collector, and this actually has a linear regression calculator built into it. So if I were to click here and dump the values into that and hit click on submit data, it'll actually give me the scatter plot. It'll give me the sample size, it'll give me the mean, it shows you the intercept, obviously the slope, and there's your equation. And the same thing appears if you want the correlation coefficient. See, if you want the correlation coefficient, you don't have to do much, you just click on it and give it a minute, and there you are, same thing. So as far as your question is concerned, the 0.045 would have to be a predicted value that you achieve if you're at this point. Let me get this up. So you were asking me where was the 0.045 calculated. That 0.045 is not calculated. Okay, that 0.045 is I'm not quite sure here what's going on with this. So you're doing the confidence interval. I think that's where you're at now. So same thing would apply with the calculator. So let's see on my calculator, if I go to stat test and I go to line right t-int, see what I get. We're looking at 98% confidence according to what you're saying. Alright, so we'll go down to calculate and hit enter. Let's see if the 0.045 comes in. So, okay, they're both negative. So that means that this confidence interval is going to sit between negative 0.6769 and negative 0.258. Notice that the b value is still the slope, and it's still negative. There's your a value, the 31. There's your same value for the standard error. So the 0.045, let's experiment what happens here. If I were to take, let's see, that looks like the margin of error is what I'm thinking about here. That's what I'm suspecting. Because this this would have to be the margin of error. I'm looking at the negative 0.4671. That's obviously your slope. So it's the slope plus or minus, looks like the critical t-value. Okay, and then this 0.045 should be the standard error. Right, and so it says here, know that that is the 45.41, but I am lost as to how the standard error is calculated. Okay. Alright, so let's look at it this way. Alright, so to get more specific, let me just go back and let's just look at this from the perspective of how you actually calculate the standard error. So in your calculator, you remember that you got part of your output is S, which is the standard deviation for this model, which is 191.2828.986, right? And that's right here as well. What you need to do is divide this by the square root of the value. So you start with the 58 minus the mean of 60.6, and you're going to square it. That you'll see here. All of this is this part. Okay? So you'll have to calculate this, take the sum of it, and once you take the sum, which is 17.2, that's what I got, you're going to write this down under here as the square root of 17.2. When you divide this value, the 0.191 by the square root of 17.2, that's where the 0.046 comes from. It's not 0.045, I don't know where you're getting that from. I prove it up here, because I went backwards and I proved it, and I said, well, if I add these two values and divide by 2, I should get the actual value for the slope, which is right here. The critical value, obviously we look up in the table, degrees of freedom 2, and alpha value of 0.04, two-tailed, or 0.02, okay? And you did that correctly, there's nothing wrong with that. This is what you just calculated, that's all of this jazz down here. Okay, with that said, if I prove it backwards, you notice that the distance, the margin of error here between these two values is 0.209 on both sides, 0.209. Notice that when I take that critical value, the 4.541, times the value that I obtained here, which is the critical 0.046 that we were looking for, the standard error, when you multiply those two, notice that you get that margin of error. And that's what your question is, I believe. Okay, so you see the whole picture, you see all the tools and resources you have available. Unfortunately, this, if you want to look for it the hard way, you're going to have to calculate it yourself manually. Very few technologies actually provide you that calculation. Hope this was helpful. Sorry for the lengthy discussion.